All right, guys. So we talked about the sinusoidal source in the last section. Said that both voltage sources and current sources from now on will not be DC sources. They will not be constant. They will be time varying with a particular mathematical form. And we want to take a look very quickly at a circuit that contains a sinusoidal source. I'm going to mention a few results without proof, but we're essentially taking kind of a global look at where we're actually headed in this chapter in taking a look at this example. So for the next section, I want to talk about the sinusoidal response. And as an example, we're going to take a look at a circuit that you've seen before. We're going to look at an RL circuit. So suppose that we have an RL circuit that looks something like this. There's a voltage source here that's providing us with a voltage V sub S as a function of time. And we then hook this up to a switch. Now, the switch is open for a very long time, and at t equals 0, we close the switch. The rest of the circuit is also hooked up to a resistor over here, as well as an inductor there, characterized by an inductance L. And there's going to be a current here of interest that's flowing through both a resistor and the inductor and even the voltage source. Keep in mind that all three of these elements are in series, therefore the current in each one of the elements must be the same at all times by KCL at any of the nodes. Now, the particular form of the voltage source that we've actually dealt with up until now has been constant, right? But now we actually want to switch gears and say that the sinusoidal source is the one that we had previously described, and it takes on this particular form, right? Now, one of the things that we can do quite easily is by using the IV characteristics of the resistor and the inductor, as well as KVL, we can actually write down a differential equation that describes to us how these particular parameters are changing as functions of time. So over here, for example, like if I concentrate on the circuit, notice that across the resistor, staying consistent with the passive sign convention, there is a voltage across this resistor that I can write like this with that polarity. There's also a voltage across the inductor that I can write with this particular polarity, noting that the current that's flowing through the inductor has to be the same as the current flowing through the resistor. And that same current is also going to be flowing through this voltage source as soon as the switch is closed at t equals 0. Now, notice that we can actually define a loop here, and we can still use KVL around this loop. So if I use KVL around the loop, what I'm going to do is I'm going to add up the voltages around the given loop, and they must add up to 0. Now, suppose that I start with the switch closed. I start over here, and then I move around my loop, going through the resistor first, followed by the inductor, and then followed by the voltage source. Notice that I can complete my loop by adding V sub R plus V sub L, and then minus V sub S. So here, immediately, by adding those voltages around the loop, I can say that this is plus V sub R plus V sub L minus V sub S, which is a function of time, and that has to add up to 0. This is going to be my equation 1. Now, by the IV characteristics, for both the resistor and the inductor, in other words, Ohm's law, as well as the IV characteristic, I can rewrite the above equation in the following way. So we know that for a resistor, the voltage across the resistor is related to the current times the resistance through Ohm's law, like this, while for the inductor, the voltage across the inductor is the inductance times the time rate of change of the current. So both of these I can use in equation 1, and I can rewrite that equation in the following manner. I have R times I plus L di dt. I can then add this to the opposite side, as well as use the definition for the sinusoidal source, combine that into one step, and what I get is that this is Vm times the cosine of omega t plus phi, like this. Now, this equation, even though it's nice and tiny, right, is the fundamental equation that governs the behavior of this system, this circuit. Notice that it is a first-order ordinary differential equation with constant coefficients that happens to be inhomogeneous. It's a big mouthful, right? But it just describes to you the type of equation that we're actually dealing with. And this equation itself, if solved, so when this equation is solved, it will give us how the current in the circuit changes actually as a function of time for all time, right? So it's a very important equation. Now, one thing that I'm going to do is I'm going to tell you right now, without proof, what the actual full solution is. So the full solution to equation number 2 is the following. The current, which is a function of time, is equal to r squared plus omega squared L squared in the denominator. Numerator, we have minus V sub m times the cosine of phi minus theta times e to the minus r over L times t. That's the first term. Plus the same fraction, like this, except separated by a plus sign. So we have V sub m divided by the square root of r squared plus omega squared L squared times the cosine of omega t plus phi minus theta. And this is where this theta is related to some of the physical parameters in the following manner. It is the tangent of theta is equal to omega L over r, right? Now, this is a big solution, right? Notice that it is not obvious that this actually does satisfy the differential equation shown by equation 2. That's something that I'm going to leave to you guys as an exercise to do. You should be able to take the solution, take the first derivative, multiply it by L, take that solution, multiply by R, add it together. All of the terms will completely drop out, and what's going to pop out on the right-hand side is Vm times cosine of omega t plus phi. Keep in mind that the theta will be related to the angular frequency of the sinusoidal source, the inductance of the resistance, through that given relationship as well. Now, the reason I show you this is to impress upon you that the problem itself is much more complicated than what we were expecting had the voltage source been a DC voltage source. But it is also worth noting that in the solution actually has two parts. Remember that this current is changing as a function of time. And if you take a look at the two big terms that we have here, time only appears there inside of this exponential, and it appears there inside of the sinusoid. Now, each one of these two parts to the solution has a particular name. This portion of the solution, because it is a decaying exponential, notice that it's embedded inside of e to the minus r divided by L times t. At time t equals 0, as soon as that switch is closed, right, it's going to start off at some maximum value, and it's actually going to start decreasing, 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 and going towards 0 as time starts approaching infinity. This solution, which decays exponentially over time, is what is known as the transient solution. While the other one, the time portion, appears inside of a sinusoid, right? You take cosine of omega t plus that other constant. Notice that what it does is it has oscillatory behavior, right? It never goes away. It never decreases with time, increases with time. It always stays using the same sinusoidal pattern. This is what they call the steady state solution. And the full solution consists both of the steady state solution added to the transient solution. Now, the reason I bring this up to show you the full solution to this problem is to really impress upon you that the techniques of circuit analysis that we're going to be taking a look at in this chapter, right, will not give us any information on the transient solutions. Our sole focus in introducing phasors and all of the different techniques of circuit analysis that can be used with a phasor, they will only yield for us the steady state solution, right? So the techniques of this chapter will only give us the steady state solutions. We will have to resort to other techniques. Other techniques to obtain the transient solution. Another set of important theoretical ideas and principles that are going to literally govern the behavior of everything that has to do with this chapter are the following. I'm going to state them verbally. If the input function, whether it be a voltage source or a current source, happens to be a sinusoid that looks like this, then every single other voltage and current, provided the network is a linear network, in other words, it is composed of linear elements like resistors, capacitors, and inductors, every single voltage and every single current, no matter how many components you have, will also be sinusoidal in nature. It will have the same mathematical form as that of the input function. Now, the response, in other words, the parameter of interest, whether it be a voltage or a current elsewhere in the circuit, the amplitude of the response in general will be different, right? So it's not going to have the same amplitude as that of the input. The phase constant in general will also be different. However, both the angular frequency, the frequency, and the period for every voltage and every single current inside of that linear network, they will all have the same values. So frequencies, the frequency content is always going to stay the same. Now, this fact alone, these facts taken together actually, will allow us to define a new powerful mathematical tool called a phasor, which we'll develop in the next few sections.